Hey guys, welcome back to another video. In this video, we're going to answer a burning question, that is, how are electrode potentials found, right? In the previous video, we talked about how electrode potentials affect what the products are going to be at each electrode, right? But we didn't answer the question, how do we even find the electrode potential? Where did it even come from, right? In this video, we're going to understand how to find the electrode potential, right? What does it even mean to have an electrode potential? We saw that, let's say, in case of the chloride ions, you have an electrode potential. It gets discharged, right? And due to that process of being discharged, or let's say also being charged, that is, this is actually an equilibrium. It is not a one-way reaction. It is a two-way reaction. So while some of the chloride ions are going to be discharged, some of the chlorine atoms, the molecules, are also going to break down into chloride ions, right? It's going to gain electrons. So it is actually an equilibrium. Now, this equilibrium between the chloride ions and chlorine gas results in this electrode potential. So let's better understand that with an example. Let's take a metal, that is the calcium metal, and understand how this redox equilibrium is established and how we get a cell potential or electrode potential from that, right? Okay, fair enough. So first thing, let's say you have a bar of calcium and you put that in water. Now what you're going to see is some of the calcium atoms are going to dissolve, break down, and form calcium ions, Ca2 plus aqueous, right? So what had happened is your calcium atoms, solid, turned into calcium ion and released 2 electrons into the solution. However, at the same time, what you're going to see is initially after having all the calcium ions being dissolved into the solution, some of the calcium ions are then again going to gain electrons from this electrode, that is the calcium bar, and it is going to be reduced, right? In the first case, we saw how it got oxidized. It released electrons. In the second case, we see once after a lot of the calcium atoms have been dissolved, a few of those are going to get back to the bar, gain electrons, and form calcium atoms, right? So after a point, what we're going to see is there is an equilibrium established. A better way to call this is a redox equilibrium. We can see one, oxidation, loss of electrons. We can also see reduction, gain of electrons. Calcium ions, some of the calcium ions are now going to gain electrons and form calcium atoms. Now, once the equilibrium is established, the rate of this reaction is equal to the rate of this reaction. That is, the rate of oxidation is equal to the rate of reduction. Now, you can see that once the calcium atoms are dissolved and the equilibrium is established, there is a net difference of charge between the calcium bar, the electrode, let's call it the calcium electrode, and the solution, the calcium solution. So you have the calcium solution over here, Ca2 plus, and you also have the electrode, Ca. The calcium electrode has a negative charge, right? And in case of the solution, it has a positive charge. Why, you ask? Because as the calcium ions leave the electrode and go into the solution, it is releasing or leaving its electrons behind, resulting net negative charge on the electrode. And at the same time, you have a net positive charge in the solution, right? So over here, you can see an uneven distribution of charge. Now, when there is a separation of charge, if you've studied in physics, there's going to be a voltage, a potential difference between 2 points. What do you see in case of a battery? You see a potential difference between 2 points. One is positive plate, one is a negative plate, and due to the separation of charge, there is a potential difference. Now, greater the separation of charge, greater the potential difference. So I guess you are sort of understanding where we're going with this explanation, right? So first step we saw, there is a redox equilibrium. As a result, there is a net charge in either of the place on the electrode and in the solution. Great. Second step, let's understand the potential difference, right? Now, why do some metals have more negative charges on the surface compared to others? If we compare, you have magnesium ions. So you had a magnesium electrode, you had a calcium electrode. What you see over here is as the magnesium electrode, the magnesium atoms dissolve or get into the solution and gets oxidized, it's going to leave less electrons on the surface. And as the calcium atoms leave the electrode and gets oxidized, it's going to leave more electrons. Now that is because there are less magnesium ions going into the solution. There are less magnesium ions dissociating. Whereas in case of calcium ions, there are more calcium ions going into the solution, right? In that case, there is a greater amount of charge on the bar, right? Fair enough. The one thing you can say from here is the calcium ion is actually more reactive. The calcium ion is actually more reactive, which results in a more negative electrode potential. Why? The potential difference is between this electrode and this solution, right? In case of the magnesium bar or the magnesium electrode, you have a less amount of negative charge on the electrode. In case of the calcium electrode, you have a greater amount of negative charge on the electrode. That results in a greater potential. That results in a greater half cell potential. Because this is actually a half equation, that is calcium breaking down into Ca2 plus 2 electrons. This is also a half equation. Mg breaking down into Mg2 plus 2 electrons. Right? Now, in this case, what happens is less electrons are released. In this case, more electrons released. As a result, in this case, there is a greater PD, potential difference between the electrode and the solution. Lower PD in case of magnesium. Why? Because less amount of magnesiums are dissociating. So less electrons released from the surface, which is why the electrode potential lower. More positive actually. The electrode potential is more positive. And over here, more negative. That means more reactive. Great. So this is how the reactivity, how reactive a metal is, affects its electrode potential. And that is why it affects your products in case of aqueous electrolysis. In case of aqueous electrolysis, what you see is it depends on the electrode potential of each ion which is going to be discharged. So let's say you had, again, NaCl aqueous, you have Na, which is very reactive, sodium ion, which is very reactive. It is not going to get discharged in the cathode. Why? Because it has a highly negative electrode potential compared to hydrogen, which is why it remains as ions and the hydrogen takes the opportunity and gets discharged, right? Fair enough. So the difference between the positive in the solution and the negative on the electrode is known as the potential difference. Fair enough. And this potential difference is of course measured in volts. Now, as mentioned, the PD, potential difference between the calcium electrode and the solution, is greater, which is why a more negative electrode potential. Now you may argue, why is the electrode potential negative? Why is the electrode potential negative and not positive? Isn't it supposed to be positive? We are going to answer that question as well. So just remember for now, in case of the more reactive metal, more negative electrode potential, right? Which one is more reactive over here? Calcium. So which one is more negative electrode potential? Calcium. Great. So step 3, how do we calculate this electrode potential? You may advise, why not take a voltmeter? Put one end on the magnesium electrode, put the other in the solution, measure the electrode potential, the potential difference between both points, positive, negative, find the electrode potential. Now, this process is actually flawed. Because notice one thing, the probe of the voltmeter is also a metal. The probe of the voltmeter is also a metal, which is why the moment you submerge it into a solution, it is going to have its own electrode potential as well. So what's going to happen is over here, some of the ions is going to go over here, some of the ions is going to go over here. So it establishes its own equilibrium. It establishes its own redox equilibrium, which is why over here, it is not going to give you the accurate reading. It is not going to give you the accurate reading, which is why this is not a possibility, which is why we don't do this. Now that is also why we do something more interesting. That is, we use a reference cell. Remember, in the first video, we talked about how the hydrogen cell or the hydrogen ionic equation, half cell equation, has an electrode potential of 0 volts. Why is that the case? That is because we consider the electrode potential of the hydrogen half cell to be of 0 volts. We take that as a reference point. We take the electrode potential of H plus turning into H2 gas, H plus, where is it? Did I write? Yeah. So we consider this to be 0 volts. And compared to this, we make a judgment of whether the other electrode potential is more negative or more positive. How do we do that? Let's see with an example. Right? So we find the potential difference between the hydrogen cell, H2 cell, and the magnesium cell. That value becomes the standard electrode potential for magnesium, right? So if I want to find the electrode potential of magnesium and magnesium 2 plus half equation, or this reaction, if I want to find the electrode potential of this equilibrium, what am I going to do? I'm going to compare this redox equilibrium with another redox equilibrium that is between hydrogen and H plus ions. So I'm going to compare the electrode potential of both and going to use a voltmeter now to see the potential difference between both, right? I'm going to compare the potential difference between, let's say, the magnesium half cell and the hydrogen half cell. Now what that's going to help me is, how that's going to help me is, I'm going to get a relative electrode potential. That is why in the first video, the definition was in terms of relative standard electrode potential, right? I'm going to find the potential difference between this half cell and this half cell. How does that work? Let's see. So you're going to put the magnesium half cell, that is the magnesium electrode. You have your magnesium ions, right? And you're also going to have your hydrogen half cell. This you probably don't know as of now, but it's basically you're going to supply hydrogen gas over here, right? This is a funnel, sort of a funnel, and you're going to supply hydrogen gas, and you have a solution of H plus ions, right? You have a solution of H plus ions, and you have platinum over here, which is unreactive metal, so it's not going to interfere with our reading, right? So this platinum ion acts as a surface where the hydrogen, the charge can accumulate on, and the hydrogen ions can get discharged. So over here, the electrons are going to accumulate, and the H plus ions are going to be able to gain the electrons and form hydrogen gas, right? So this platinum wire and this platinum plate acts as a surface area for the reaction to take place, right? For the discharge to take place, right? So on one end, what you have the hydrogen ion half cell. On the other, you have magnesium ion half cell. You have two half cells. You have connected in using a voltmeter. And you also have a salt bridge. What's the purpose of salt bridge? I'm going to explain later. But in short, what it does is it makes sure there is a solution. There is, let's say, potassium nitrate over here, right? Over here, there is potassium nitrate, KNO3. And how that helps is it's going to, let's say, if your magnesium ion solution over here decreases, the anions are going to go over here and keep the concentration constant. I'm going to again explain this later. But in short, it keeps the concentration in each solution constant and makes sure the concentration doesn't change, right? So what we are doing in this step is we are joining two half cells together using a voltmeter, and I'm going to measure the potential difference between this half cell and this half cell. And now I'm going to see a reading. That is, the potential difference between these 2 points and potential difference between hydrogen gas and the H plus ion concentration is going to result in a net potential difference between both of these half cells, right? That is going to result in a potential difference between both of the half cells. And in case of magnesium ions, that reading turns out to be minus 2.38. So when you connect both the half cells together, you see a reading compared to your hydrogen half cell. So this is actually your relative to hydrogen half cell electrode potential, right? So in comparison to hydrogen half cell, what is the electrode potential of magnesium ion half cell? So that is why we call it standard electrode potential. That is the definition of standard electrode potential, that in comparison to a standard hydrogen half cell, what is the electrode potential of, let's say, magnesium, let's say calcium, let's say any other metal. So standard electrode potential defines what the electrode potential of any of the metal is in comparison to a standard hydrogen half cell. Now, what does standard hydrogen half cell mean? The meaning behind that is you're going to have 1 mole per dm cube concentration of H plus ions. You're going to have a pressure of 298 Kelvin. You're going to have a temperature of 298 Kelvin and a pressure of 1 atmospheric pressure. Granted, all of these conditions are met, that is going to be your standard hydrogen half cell, right? Now, side note, this is actually how you're supposed to draw a cell that is between two half cells. How are you going to find the electrode potential? You're going to draw the diagram in this manner. You're going to have a half cell of a metal, in this case at least, a metal ion half cell. You're going to connect it to, using the voltmeter and salt bridge, you're going to connect it to a hydrogen H plus and hydrogen ion half cell, right? And this is also called non-metal and non-metal ion half cell. Non-metal ion half cell, right? Fair enough. So this is how you're going to draw it. A few things to keep in mind: draw the electrode, draw the solution, remember to write the solution as 1 mole per dm cube, right? Mg, that is magnesium sulfate, you're going to write it as 1 mole per dm cube of magnesium sulfate, because you want 1 mole per dm cube of concentration of Mg2 plus. That is all, 1 mole per dm cube. And you're going to connect it using a salt bridge, label it as salt bridge. You're going to have a voltmeter. If you want, label it as voltmeter. And you're going to have this funnelish shape through which you're going to have hydrogen gas passed in, and you're going to label it as hydrogen gas. You're going to have a platinum wire. This thin pink wire is the platinum wire, which connects it to the platinum surface. This platinum surface acts as the place where the reaction takes place. And again, I didn't write, but you should write 1 mole per dm cube of H plus concentration, right? These few things keep in mind while drawing the cell, right? Now, we're going to answer an important question, that why is the electrode potential negative, right? In case of magnesium and calcium, we saw the electrode potentials are actually negative and not positive. So why does that happen? Let's understand, right? In case of, let's say, this previous example where the cell is between magnesium half cell and hydrogen half cell, what is happening is there is a greater accumulation of negative charge or electrons on the magnesium electrode, and there is a less accumulation of electrons on the platinum surface of the hydrogen and hydrogen ion half cell, right? Less amount of charge, greater amount of charge, right? Now, you know, hydrogen over here has electrode potential of 0 volt, whereas the half cell of magnesium and magnesium ion has an electrode potential of minus 2.38. So the more positive the electrode potential, the greater the chance of it being discharged and gaining electrons, because it's more positive compared to minus 2.38. It is more positive compared to minus 2.3, right? So it's going to gain electrons. So it's going to gain 2 electrons from hydrogen gas, right? So what is happening over here? Gaining of electron is going to be reduction. So over here, reduction. The other thing is, over here, it's going to be oxidation. Why? Because due to the more negative electrode potential, it is going to release the negative charge and it is going to release the electrons, right? It is going to release the electrons and form magnesium ion. So you can write it as Mg2 plus 2 electrons, right? It is releasing the electrons. Oxidation is taking place. Now, what do you know about oxidation? Where does oxidation take place? Oxidation takes place at the anode, right? At the anode, you release the electrons, right? You release the electrons at anode. Where does reduction take place? At the cathode. At cathode, remember, you always gain electrons. Gain electrons. However, you may be confused in this case. Why? Because there is a greater amount of negative charge over here. So how is this the anode? And how is this the cathode? Isn't there a more negative charge accumulation over here? Now, don't be confused by that. The main purpose of saying all of this is, don't be confused by where the greater amount of negative charge is. The point is, wherever you see oxidation taking place, that is going to be your anode, just based off that one factor. If you see oxidation taking place, anode. If you see reduction taking place, gain of electron, that is the cathode. So over here, this is going to be your cathode, right? So electrons are actually flowing from over here in this direction, from this anode to this cathode, where reduction is actually taking place. Although there is a greater accumulation of negative charge over here, this is going to be your anode because oxidation is taking place over here, right? So in reality, negative terminal and positive terminal. However, this is going to be your anode, where it is going to have a greater accumulation of negative charge, and you're going to see oxidation taking place, right? Fair enough. Now, if we see another example over here, what you have is you have the copper and copper iron half cell, and you have what you call it, the hydrogen and hydrogen ion half cell, right? So in this case, what you're going to see is the copper is less reactive actually. And if you look at the electrode potential, did I write the electrode potential of it? Most likely not. But copper actually has a more positive electrode potential, that is something, let's say 2 volts, positive 2 volts of electrode potential. This is going to have a positive 2 volt of electrode potential compared to the hydrogen half cell, which is 0. Which is why in this case you see less amount of charge on the copper electrode. And in case of this platinum surface, you see a greater accumulation of negative charge. However, why is the electrode potential positive in this case? That is due to the fact that there is a less amount of electron accumulation on the copper electrode, because less amount of coppers are dissociating into the solution. That is why it has a more positive electrode potential, because it is gaining electrons from the hydrogen and hydrogen ion half cell. So electrons in this case are going from the hydrogen ion half cell and reaching the copper and copper ion half cell, which is why its electrode potential is going to be something very positive compared to the hydrogen and hydrogen ion half cell. So less amount of negative charge on the copper electrode, which is why it is going to pull the electrons from the hydrogen and hydrogen ion half cell, which is why copper will have a positive electrode potential. Now, in previous cases, what you saw, the hydrogen ion was actually gaining electrons from the magnesium and magnesium ion half cell, which is why magnesium has a negative electrode potential. So, in summary, we can say the electrode potential will be positive when H2 gives electron. In this case, H2 is giving electron. And when the electrode potential is negative, H2 gains electron. Now, the correct definition of electrode potential is going to be the voltage measured for a half cell compared with another half cell. Now, what is the standard electrode potential? As somewhat mentioned, the voltage produced when a standard half cell ion concentration of 1 mole per dm cube at 298 Kelvin is connected to a standard hydrogen electron under standard condition. Therefore, when you have a standard half cell, that is, let's say Mg, and let's say this Mg, and a solution of Mg2 plus of 1 mole per dm cube, this is the standard half cell connected to another standard hydrogen electron where there is a H plus concentration of 1 mole per dm cube, a temperature of 298 Kelvin, and a pressure of 1 atmospheric pressure. In that case, the cell potential that you get between the hydrogen and hydrogen ion half cell and the magnesium and magnesium half cell, that is going to be your standard electrode potential of magnesium. Because you're measuring the magnesium half cell against the hydrogen half cell, right? So that is the definition of standard electrode potential. Great. Now these are a few values of electrode potential, half cells and their electrode potential. So you can take a look at it, and you're going to see, in case of, let's say, calcium, right? In case of calcium, you can see it is negative. It is highly negative. That means, what does that mean? According to this, electrode potential is negative. That means hydrogen ions are going to gain electrons and produce H2, right? Hydrogen ions will gain electrons in that case, which is why the electrode potential of calcium, notice, is negative. Great. So that is in summary what cells are and how do we find electrode potentials, and see you in the next video.